Alright, Chapter 7, number 49. A particle of mass 1.18 kilograms is attached between two identical springs on a horizontal frictionless tabletop. Both springs have spring constant K and are initially unstressed. Part A, the particle is pulled a distance x along a direction perpendicular to the initial configuration of the springs as shown in figure 7.49. Show that the force exerted by the springs on the particle is given by the following equation. Part B, show that the potential energy of the system is given by that equation. And part C, make a plot of the potential energy versus x and identify all equilibrium points. Assume length to be 1.2 meters and K constant to be 40 newtons per meter. And part D, if the particle is pulled 0.5 meters to the right and then released, what is its speed when it reaches the equilibrium point x equals 0? And here we have our figure 7.49.
Okay, so for the sake of time, I've drawn three things, so you guys have to watch me struggle to draw them. This is the diagram from the book, which I'll explain in a second. This is just that triangle in here, which we'll use to solve for a few things. And this is the sum of the forces. This is our free body diagram. So basically what's happening is we have two springs that are coming at each other like this, and then somebody's taking the ball here and pulling it that way. So the ball is getting stretched this way, and it's getting stretched a distance x. Our springs are also getting stretched some amount, right? And then that's going to create stored energy in the springs, which we're going to try to find out, and the energy is exerting a force on the particle, and we are asked to find the force of the particle and the potential energy of the system. So our first step is the force on the particle. So the force on the particle, we're going to sum the forces in the x direction, because if I were to sum the forces in the y direction, I would get this equals that, and we already know that because they're identical springs. So we're going to do the x direction. And we can see we have k negative, because I'm going to call this negative and this positive, and I'll draw it the other way. I'll do this plus y plus x. So negative k delta x cosine theta minus k delta x cosine theta. So we get negative 2k delta x cosine theta. Alright, our first thing to do is to find the change in the x direction. And it's not just this, it's not just x. What we have to use is the change in the spring. So we're stretching the spring a certain amount. But how much are we stretching it? Well, originally it's at a length of L. Now it's at a different length, and that different length we can find with geometry. This hypotenuse is going to be x squared plus L squared. So our new length of the spring is x squared plus L squared, and our original length is L. So our delta x for the spring is going to be given by square root of x squared plus L squared minus L. There's that. We can also use this picture to find cosine theta. Cosine theta, according to our picture, is going to be x over square root x squared plus L squared. So we're going to take that all and we're going to make our big equation. Force of the springs is going to be equal to negative 2k delta x is square root x squared plus L squared minus L times x over x squared plus L squared. And what this is going to do is, if we're given L and we're given x, we're going to have a function of our force as x increases or decreases. We're going to be able to figure out the force at each different x value. So if we do some algebra to solve it for what we're looking for in this equation, I'm going to put the x over here. So negative 2kx, that cancels out, becomes 1 minus L over x squared plus L squared. And that's f as a function of x, because we know k and we know L. And if we're going to use this as a vector form, so if we make this a vector, this was in the x direction only, so it's going to be an I hat vector. That is step 1. Now I'm going to erase this and put the force up here, smaller, so we can use it for future reference. 1 minus L. Okay. Our next step is to find the potential energy of the system. So, the potential energy, the stored energy, can be given by, so originally when there's this, the springs are not taught at all, so there's no potential energy. So all of our potential energy is going to come from these springs. And the springs, the potential energy added is going to be the work done by the force to move those springs that far. So the work done by the force is given by the integral of f dx. So our potential energy is going to be the work of the two forces. So we have, this is going to be our initial 0 points from 0 to x of f dx, and this is calculus. We're going to integrate this to find our function of potential energy. So that is going to expand to 0 to x of negative 2kx times 1 minus L over square root of x squared plus L squared dx. Alright, how do we integrate that? Well, we're gonna take this negative 2k out, and then we're gonna distribute the x. So we have negative 2k 0 to x for negative x plus xl over x squared plus L squared. Remember, when we have dx on the side here, that means everything besides x is a constant. So we're going to ignore the l's, and we're going to be just looking at x. So what I'm going to do is I'm going to split this into two different integrals. So we're going to have integral 1 over here, which is going to be 2k 0 to x dx, distributing the dx, and then we're also going to have minus 2k 0 to x xl square root of x squared plus L squared dx. And I don't know if you can see this or not, but do some really hard thinking and you get 1/2 x squared from 0 to x. And for the other side, you get something a little bit trickier. Well, it actually works out pretty well. You get the square root of x squared plus L squared. The reason for that is, if you can imagine, oh, I'm going to take that L out, by the way. I forgot to take that L out. The reason for that is, so x squared plus L squared, if you take the derivative, you get 1 over, so the derivative of x square root x squared plus L squared, f of x equals f prime of x equals, that goes on the bottom, 2 square root x squared plus L squared. So normally it would be 1, but we have a chain rule with x squared here, so that becomes 2x, and then the 2's cancel. So we have x over square root of x squared plus L squared. So that's where that integration came from. If you guys haven't taken calculus, you'll probably get more comfortable with integration later. We're going to plug that in. We're going to get 2k times 1/2 x squared minus 2kl times square root of x squared plus L squared minus the square root of L squared, because we have to plug in 0 for x as well. Over here I didn't do that because 0 is going to equal 0. I'm going to put that up here just to make it simpler, and we get kx squared plus 2kl times L minus square root of x squared plus L squared. And that is the equation for potential energy. So there we go. Integrate the force and you get the work, and in this case the work is going to be our potential energy, because all of the energy in the system is going to come from pulling those springs. So our next step is to graph this given our values of x and L. So I had my equation, potential energy is kx squared plus 2kl times L minus square root of x squared plus L squared. Now they give us some values. L is 1.2 meters, K is 40 newtons per meter, and we know that the mass of the object is 1.18 kilograms. So they want us to graph potential energy as a function of x, so our function is going to be 40x squared plus, if you plug that stuff in, you get 96 times L, which is 1.2, times 1.2 minus the square root of x squared plus 1.44. If you graph that, you get a function that looks kind of parabolic, but is flatter at the bottom, and then it just gets bigger. The reason for that is because when it's near 0 here, this function dominates, and when it's far away from 0, this function dominates. So our equilibrium point is wherever we have the lowest amount of potential energy, which is there. Potential energy is 0, that means equilibrium. So our u of x equals 0 at x equals 0. So that's our equilibrium point. And now they want us to find out the speed when it reaches 0 after it's released from 0.5 meters. So using this equation, that's our potential energy. We know that the kinetic energy initial plus the potential energy initial equals the work, plus the work equals kinetic energy final plus potential energy final. We don't have any initial kinetic energy, and we don't have any final potential energy, and we don't have any work. We have no force besides the springs, but that's our potential energy. So we have no outside force that's doing any work on our system. Our potential energy is going to be this equation, and x is going to be 0.5 meters, because that's how far we're pulling the string and then releasing the particle. Well, not the string, but springs and then releasing the particle, and that's going to equal kinetic energy final. So plug all that in. So plug all this stuff into here, and you'll get 0.4 joules equals 1/2 m, which is 1.18 mv squared. So V is going to come out as 0.823 meters per second.